Okay everyone, let's try to solve a more involved problem here. It's actually out of the night book. It's on page 52, chapter 2, example 2.13, the motion of a rocket sled. A rocket sled accelerates at 50 meters per second squared for 5 seconds. Then it coasts for 3 seconds. Then it deploys a braking parachute and decelerates at 3.0 meters per second squared until coming to a halt. A, we want the maximum velocity of the rocket sled. B, the total distance traveled. There's a 4-step process that the night book talks about. It's a nice model. It's a nice way to solve a problem. And the first thing you do is you model. You basically model the situation. Then you visualize. You visualize the situation. Next, you solve. You solve for your unknowns. And finally, you assess your answers. And this is discussed in some detail. This 4-step problem-solving approach is discussed in details earlier in the night book, and you could find that and read about it, and I'll let you know exactly what that is tomorrow in class. Now, let's think about what's happening here. We've got acceleration, and when we're coasting, there's no acceleration, it's constant motion, and finally we have a negative acceleration when we come to a halt. So this problem has 3 parts to it. Okay, and let's see if we can visualize this a little bit. We can model the sled as a particle, or we can draw a sled, whatever you prefer. I'm going to use it as a particle, just to keep it simple. There's the sled modeled as a particle, and initially we're going to move to the right, like so. And and this is going to be the first part of the motion. And what we're going to say here is that basically we know the following: that the initial velocity is 0. We're accelerating from rest, that's the assumption. The acceleration is given as 50 meters per second squared, and the time over which this occurs is 5.0 seconds. So we accelerate across, let's assume, a flat surface, one-dimensional motion, and then we reach a point where we'll draw the sled again, and this will be the second part of the motion. And this is when the sled is moving in this direction, and basically it's going to reach Vmax at this point. Okay, so we can let this arrow represent Vmax if you'd like, and that's one thing we need to find. We need to find Vmax, what it equals. Okay, and once we reach Vmax, if we call this the second part of the motion, once we reach Vmax, okay, the acceleration in this part, once you achieve Vmax and you're coasting, the acceleration, we'll call this acceleration now equals 0 meters per second squared, and this lasts for a time of 3 seconds. Okay, now this Vmax, I'm going to call it, you can think of it as a final velocity in the sense that it'll fit a formula. So finally we're going to coast for 3 seconds at a much higher velocity, and then eventually we're going to get into a braking phase. Okay, so here we have a positive acceleration. Here's when we are coasting, and finally this is where we have in this last stage, I'll draw an arrow here again, and this will be when we'll have a negative acceleration and we'll be braking to a stop. And finally we'll show that over here. There's the sled modeled as a particle. And a couple of things that we need to think about here in this part. This Vmax will end up being this will become the initial velocity as we slow down. And if we come to a halt, the final velocity will equal 0. And you're telling us that the acceleration in this part, we are decelerating. That's a word that's not often used. It's usually just referred to as a negative acceleration. You're slowing down. So this would be a minus 3.0 meters per second squared. And the time is unknown, but we may not need to worry about that. Okay, well, let's see what we can figure out here. First of all, let's figure out this maximum velocity, V max. Now the question is, do we have enough information to start with? And it turns out, well, we know the initial velocity is 0, the acceleration is 50 meters per second squared, and the time that this occurs to get up to V max is 5 seconds. So we have plenty of information. This would actually be, we would find this using equation 1, and that equation is basically going to be that Vf equals A times T plus Vi, and Vf is obviously going to be V max. Working out the numbers, we will find that we will have 50 meter per second squared times our time of 5.0 seconds plus 0 meters per second. And the math is not hard. 50 times 5 gets us 250. The seconds will cancel with just meters per second. So we're going to get a velocity of 250 meters per second. Okay, simple enough. Now, the next thing we want to figure out, what we're after in part B is the total distance traveled. Well, to get the total distance traveled, we've got to find three displacements. The displacement during the positive acceleration, then the displacement while we're coasting with no acceleration, and then the displacement as we slow down and come to a halt. So let's find what we're going to call delta x1. And let's think about it. We know the acceleration, we know the initial and final velocities, we know the time. We have a couple different options here. I'm going to pick equation number 1. Okay, this was equation 2, by the way, up here, to let you know. Let's pick equation 1, which is basically delta x is going to equal 1/2 AT squared plus VI times T. Now, to use this equation, I'm going to scoot this up a little bit for you. To use this equation, we're just going to put in what we know. Now, recall that the initial velocity equals 0, so this part I don't even need to worry about. So all I need is 1/2 times A times T squared. That's going to be 1/2 times 50 meters per second squared times the time, which is 5.0 seconds squared. And we get 1/2 times 50, which is 25, and 5 squared is 25. So we're going to get basically 25 times 25, which is going to give us 625. And the units, this is going to be seconds squared. The seconds squared will cancel. We'll get the first displacement during the initial acceleration is 625 meters. Okay? Delta x2, how will we get that? Well, we have no acceleration. We're coasting essentially at a constant speed of 250 meters per second. We need the constant motion equation, which would be delta x will equal the constant velocity times the time. Well, the velocity is the velocity that we got up to. This maximum velocity is maintained for 3 seconds. So that's going to be 250 meters per second times a time of 3.0 seconds. And we see that that, in and of itself, gives us 750 meters. That's the additional displacement during phase 2, you could call it, during the coasting phase of this rocket sled's motion. Finally, delta x3, the displacement as it comes to a halt, as it slows down at a rate of minus 3 meters per second squared. Now think about it. We know that the velocity is going to be 250, right here. This is 250. It's the maximum velocity that was maintained until we started to slow down. The final velocity is 0, and the acceleration is minus 3. Now we don't know the time. Well, maybe we don't need to bother finding the time. If we know the two velocities and the acceleration, and we want to find the delta x, that would lead to equation 4. Okay, so equation 4, everyone, solve for delta x. Equation 4, scoot this up so you can see what I'm doing. Equation 4 basically is delta x will equal the final velocity squared minus the initial velocity squared over twice the acceleration over 2a. Putting in the numbers, we know this is going to be 0 squared. The final, we come to a halt, that's 0. Minus, this is going to be 250 meter per second, but that has to be squared over 2 times the acceleration, which is a negative 3.0 meters per second squared. Okay, if we do some number crunching here, we will find out. Bring our trusty calculator into the mix here. We'll take 0 squared. Let's turn this thing on first. Clear it. 0 squared minus 250 squared. Now I like to get a number at this point. That's going to be minus 62,500. That's meters squared per second squared. We're going to divide that by 2 times negative 3, which is going to divide that by minus 6. Minus 6.0 if we want to put in a, and we're going to get that this is, wow, it's going to be 1,417 meters. Now you might be asking yourself, well, that's such a much larger distance than the first 2 phases of the motion, and well, is that realistic? Well, the numbers seem to be true. I don't think we made a math error. I don't think we made an algebra error. I think we got all the numbers right. Our thinking is good. So what we want basically to figure out the total distance traveled. So we're going to have to add up delta x1 plus delta x2 plus delta x3. So we'll take 1,000, let's clear this out, 1,417 plus 750, and then also plus 625. We get a grand total of 11,000. So delta xt, the sum of all the 3 displacements, is 11,792 meters. That rounds to 3 sig figs to 11,800 meters. Okay, well, that seems like a pretty long distance. I'm wondering if this is, again, we visualized, we've solved, we've modeled things with constant motion and uniform acceleration. We've modeled the sled as a particle. Now, does this answer this distance? Is it realistic? So this is when we have to assess our work and its meaning. So the first thing to think about, well, this 250 meters per second, this V max, just how fast is this in terms that you and I can understand? Well, I'm going to use the calculator, and I'm going to go to the side tools. I'm going to scroll up to that. I'm going to go into the unit converter. I'm going to go to 6 velocity, and I'm going to convert it to miles per hour and see how fast is this sled moving. Okay, if it's a rocket sled, it's probably moving at a pretty good clip. So everybody, I'm going to take, it's already in units of meters per second. I'm going to type in 250. I'm going to press enter. And what it does, it puts it into scientific notation. It's 2.5 e to the 2 meters per second. We're going to convert it to its equivalent in miles per hour. I'm just going to press enter. Well, it took it all the way to knots. Not too good. Move back. Okay, this converts to, now check this out, it's e to the 2 at the end. So this is over, that's 5.59 e2 miles per hour. That's 560 miles per hour. So this is equivalent to 560 miles per hour. That's awfully fast. That's very fast. Now this is a sled, and if it's on a track, like railroad track, or even if it's, that's probably how they used to do these things, I believe. That's a top speed of 560 miles per hour. And now let's think about, what's this total distance in miles? Let's check it out. We have delta xt, which is 11,800 meters. Okay, and let's do a conversion of that. I know off the top of my head that 1 mile is 1,609 meters. Just I remember crazy facts like that. So the unit factor of conversion would be 11,800. Okay, I'm going to get us out of this. I'm going to hit exit. I'm going to take 11,800 divided by 1,609, and I'm going to get it 7.3 miles. This is so 7.3 miles the total displacement. So, well, rocket sleds, when you accelerate, think about it, the acceleration, the deceleration is -3. We accelerated at +50. How much more is that? Well, if I take 50 and I divide it by 3, if I take 50 divided by 3, that tells me I had almost 17 times the acceleration phase is 17 times greater than the deceleration. So you're accelerating at, actually this is about 5 Gs. And the deceleration is about 1/3 of a G. So it's pretty intense. So given the fact that the acceleration to slow down is 1/16 or 1/17 acceleration to get up to maximum velocity, it's really pretty logical that it takes over 10,000 meters to bring this thing to a halt. And remember, you're up at over 500 miles per hour, and it takes you most of the journey is slowing the thing down. So there's the problem solved the way I would do it. Okay, and it's pretty cool. I like this kind of problem.